The next problem which we have is also an easy problem, provided you have got all the concepts of limits, the right hand limit, the left hand limit, etc. We need to find the values of p or the range of p or the intervals in which p may lie, such that the function fx equals x bar p into cos of, this is 1 by x, is continuous at x equals 0, which is the first part, and differentiable at x equals 0, which is the second part, and the value of function at x equals 0 is given to be 0. Now in order to proceed with the first part, which is continuity, we know that a function is continuous if the left hand limit is equal to the right hand limit at that point is equal to the function's value at that point. So we know f of 0 is equal to 0. So we've got first part. Now we need to find the right hand limit at x equals 0. This will be equal to limit h tending to 0, 0 plus h, which is equal to h par p cos of 1 upon h. Now we know that this has oscillatory limit, and we need to find the limit and make it equal to 0, since the limit at x equal to 0 should be equal to the function's value at x equal to 0. So this should be equal to 0. Now this can be 0 only if p is greater than 0, because if p is negative or 0, if p is 0, this will vanish, this will become 1, and this will have oscillatory limit, so this cannot be continuous. And if p is negative, then this h bar p will go in the denominator, and then it will be a discontinuous function. So p should be greater than 0 for right hand limit be equal to f of 0, and hence for the continuity of the function. Now let us check the function's left hand limit at p greater than 0. We need to have left hand limit should be equal to right hand limit. So checking left hand limit at x equals to 0, we get limit h tending to 0, 0 minus h. So this is equal to minus h par p cos of 1 upon h. Very clearly from here also p should be greater than 0, because at p greater than 0 there will be a term of h in the numerator, and hence at h tending to 0 the limit will become equal to 0. Hence the answer for the first part, that is for the continuity of function at x equal to 0, we need to have p greater than 0. So this is the first part's answer. For the differentiability part, we got to have the left hand derivative at x equal to 0 should be equal to the right hand derivative at x equal to 0. The right hand derivative becomes limit h tending to 0 f of x plus h, which is equal to 0 plus h bar p into cos of 1 upon h minus f of 0, which is equal to 0 upon h. So this becomes equal to limit h tending to 0 h bar p minus 1 cos of 1 upon h. Now very clearly, for the left hand derivative to be equal to right hand derivative to be equal to a finite quantity, this should be present in the numerator, a term of h, because this is again having an oscillatory limit. So for h to be present in the numerator, p minus 1 should be greater than 0 or p should be greater than 1. Now let us check whether left hand derivative is also coming equal to right hand derivative for p greater than 1. The value of right hand derivative is coming out to be 0. Now the left hand derivative comes out to be limit h tending to 0, 0 minus h, which is equal to minus h par p cos of 1 by h minus 0 upon h. Now this becomes equal to limit h tending to 0 minus h par p minus 1 cos of 1 upon h. Now very obviously for p greater than 1, the left hand derivative is also coming equal to 0. So the left hand derivative is coming out equal to right hand derivative equal to finite. Hence the function is differentiable for p greater than 1. So our final answer for the first part, that is the continuity part, is p should be greater than 0, and for the second part, that is the differentiability part, p should be greater than 1, and this is our final answer.